Hello to all physics enthusiasts and fans of physical experiments. This is Andrei Shetnikov, and our current video will be dedicated to a toy called the helicopter toy. When I was in the 3rd grade, I joined an aircraft modeling club. First of all, we made ourselves some sharp knives, and then we carved a propeller from a wooden block of wood, mounted it securely on a stick, and went to launch it in the yard outside. But now, however, I have a plastic propeller, and it is also securely mounted on a stick. The stick is long enough so that the Janibekov effect does not come into play. By the way, we have a separate video about it. And if you spin the stick with your hands, the little helicopter takes off with your hands. And this device turned out to have quite fascinating physics, which we want to share with you all. Here is one of the launches we did outside. Everything happens very quickly. So let's slow down this video just a bit more slowly for clarity and understanding purposes. In some of our best launches we've had before now on record at least once, tracing constructs a graph that shows how the vertical projection of the helicopter's speed depends on time. It immediately accelerates to a speed of 6 meters per second, and then this speed gradually decreases. And at the same time, the helicopter's acceleration is approximately 4 meters per second squared. And since the helicopter toy moves with constant acceleration, a constant force is acting on it. What forces are acting on the helicopter? First, there is the gravitational force, mg, directed downward, and second, there is the lift force directed upward. Well, we can simply write down Newton's second law, ma equals, and here we gather all the forces. And since the acceleration was approximately 4 meters per second squared, which means it is approximately 0.4 times g, this means that the aerodynamic force happened to be 0.6 times mg and remained constant, even though in fact the helicopter was slowing down its rotation and changing its vertical speed. And that is already surprising. Then we thought that launching it outdoors is certainly good, but we definitely need to do some laboratory launches at not such a very great height to measure not only the vertical speed of the helicopter, but also its rotation frequency and somewhat more. And this red cap is specifically placed for tracking purposes. And now I am launching the helicopter. In this video, you can clearly see how the blades rotate, and we can clearly measure their rotation frequency. And if you look closely, you can actually see how this frequency gradually decreases, slightly due to the fact that air resistance. We find the acceleration at which the helicopter was moving, and it is again 4 meters per second squared. So, the aerodynamic force in this experiment is also equal to 0.6 milligrams. Now, let's see how the propeller's rotation frequency changed during the flight. It has decreased from 27 rotations per second to 13 rotations per second to 13 rotations per second. And since the rotation frequency of the propeller has decreased by half, the rotational speed of its tips has also decreased by half. And the square of the speed, which is included in all aerodynamic formulas, has decreased by a factor of 4. But we know that the lift force indeed remained unchanged. And the 4-fold decrease in the square of the speed must somehow be significantly compensated. And it is significantly compensated by increasing the angle of attack by a factor of 4 overall. The blade pitch angle of our propeller is currently 11 degrees approximately, and when the rotor spins, the air flows over the tips of its blades at exactly this angle. But when the rotor moves slightly upward, the oncoming air in its frame of reference moves downward, and the angle of attack decreases. We can find the reduction of the angle by knowing the vertical speed of the helicopter and the speed of the tips of its blades, which we will find by multiplying the circumference 2πr by the rotation frequency of the propeller F. To the angle of attack found in this way, you need to add approximately another 4 degrees, which arise due to the asymmetry of the profile. And now we see the change in the effective angle of attack over the flight time. It changed from approximately 8 to 31 degrees by a factor of 4, which significantly matches our prediction. And now we need to take another look at the flight of this little helicopter as a whole. When I spin it sharply, the blades move at a large angle of attack, and the lift force is quite significant, which throws the helicopter upwards. But the angle of attack in flight immediately decreases slightly, and in this sense the rotor can only descend further, although it does have an initial speed. It continues to move with a negative acceleration of 0.4 g, and by the way, when the rotor hovers, it is actually simply at the peak of its descent at that specific moment, in fact. And now we need to talk about the important energies involved in this process. At this point, I will hand over to Alexei.
At the start, we spin the helicopter up to a certain angular frequency O0, and it has the kinetic energy of rotational motion and O0 squared divided by 2, where I is the moment of inertia of the helicopter relative to its axis. And then it rises to the highest point, where it has potential energy mgh at its peak. Part of its rotational energy remains, which is omega squared over 2, and thus some of the energy transfers into the movement of air, causing a slight disturbance. And of course, we are interested in what portion of the initial energy can be converted into potential energy. This determines the height to which the helicopter can ascend. And that's what we're going to figure out now. To calculate the rotational kinetic energy, we need to know the moment of inertia of the rotor relative to its rotational center. But measuring this moment of inertia is inconvenient, and it is more convenient to measure the moment of inertia relative to the end of the blade. And for this, we assembled this setup. That is, the axis passes through the end of the rotor blade, I deflect it, and it oscillates with a period of 3/4 of a second, which corresponds to an angular frequency of 8.5 radians per second. And from the formula for the physical pendulum, we immediately and accurately determine the moment of inertia relative to the end of the blade using the formula mgr divided by omega squared. To find the moment of inertia at the center of the rotor, we use Steiner's theorem. This moment of inertia is less than the measured value by the amount mr squared. If we now substitute the data, the moment of inertia of the rotor is 5 × 10 to the -5 kg per square meter. As for the wooden stick, we calculated its contribution to the moment of inertia and found it to be more than 1,000 times smaller, so this contribution can be neglected. And in our indoor test, the helicopter ascended to 1.2 meters. It was at 27 revolutions, and at the highest point, the rotation frequency decreased to 19 revolutions. The initial rotational energy was 0.72 joules. The potential energy increased by 0.22, and the residual rotational energy at the highest point was 0.36 joules, thereby transferring 0.14 joules to the air. And thus the efficiency of energy investment in the indoor launch was approximately 30%. Now let's look at the outdoor launch. This time the helicopter flew much higher, reaching about 4 meters. It made 40 revolutions per second, and at the top, the frequency dropped to 22 revolutions per second. Rotational energy was 1.6 joules. Out of this, 0.8 joules were spent on the lift, which is 50% of the initial energy. 80 joules, which is 50% of the initial energy. The residual rotational energy was approximately 0.5 joules of energy, and 0.3 was transferred to the air. And look, the more I spin the propeller, the greater the portion of the initial rotational energy that essentially converts into potential lift energy. Why does this happen initially? Share your thoughts on this in the comments section of this YouTube video.